Okay, we started the central limit theorem. This is very interesting theorem because in many different situations, this random record or random process or ensemble, you could deal with different the probability function. So here is said x1, x2 through all the way through xn. And each connects, of course, this is independent random variable. This independent random variable, that's the kind of the big assumption. And independent means it's not correlated to each other. For example, one variable could relate to, for example, pressure. Another could relate to velocity. Another could relate to acceleration. Then if they are all independent, problem-wise, it's very simple, very simpler to solve. If it's correlated to each other, statistically, it's kind of the complex problem to solve. So here initially, and there are lots of also applications on that. So if you say independent variable with any probability function for each the variable. Could it be any? Could it be Rayleigh distribution? Could it be normal distribution? Could it be log normal distribution? Vice versa. But if you're dealing with many random variable, then let's say it approaches to infinity, then you can say x1 plus x2 all the way through xn, let's say equal to x, that follows or closely follow the normal distribution. You follow me? So this is a central theorem. You can, if you have only 10 random variable, you can say it follows, I just started. So I just started. So you have a good lunch? So this is kind of a very interesting. But the question, one of the assumptions here is as n approaches to infinity. That's the condition. But we never reach to infinity. That's one of the things you always have to remember. But when you deal with a large number of a random variable, then summation of all the random variable would follow the sum probability function, which we don't know. So, but if number really grows, good thing is this summation, for this summation of random variable, the probability function closely follow the normal distribution function. And let's say for the normal distribution function, there's some just additional comment. Normal distribution function you can define really well if you have two parameters. One is mean and standard deviation. That's the measure. That's the two parameters which is the measure of peakness and the dispersion of probability function. If xi is normal, x1 plus x2 and cxi are normal. So for the normal situation, For if the random variable follows the normal distribution, then summation really follows the normal distribution. Otherwise, it's not. Then you have to use something else. You have to use so-called the Pearson distribution function. Remember, it's worth to remember. If you really need a probability function, then Pearson probability function. I used this some years back in late 1960s. Even it has he published a book. So if you can find the probability function, then it may be worth to click in internet Pearson distribution. Nowadays everything is in the internet. You can just go check it out, Pearson distribution function. Then you can study a little bit. Then you can model your data using Pearson distribution function. Then that's a well-defined and bounded probability function. Then you can use it for your applications, okay? because the physical phenomena does not always follow the Gaussian distribution, okay? Remember that. Does not follow always Rayleigh distribution, even if Rayleigh distribution can handle the skewness, sometimes doesn't fit. And then you have to deal with what to do. Then Pearson can come into picture and do well. So I talked this Wednesday. Truly tail end is infinite for normal, and no random data can fit. But we can live with the finite approximation. So we can live with the small error, then you can handle that. Because tail end, you can neglect it. Gust wind, ocean wave height, not good for normal. Why? Why this is not good to use for the probability function, normal probability function? No skewness. The gust wind has a skewness in the probability function. When I say probability function, it could be probability distribution, it could be probability density function. So this is, let's say, it's at gust wind, then this is a probability density function. So if you put a lot of data in there, so then you can fit in the curve. Probability density function is something like, could be something like this. Normal distribution, you can use it. Why? I mentioned to you a few times, you can do that because this has a skewness. Right here, this is a peak point. It has a skew. It's kind of shifted to the left. It's not nicely like this, symmetric at the middle. It's not. Remember that. Okay. So this kind of the function is really, I think this is correct. I hope. Probability density function is something like this. So curve fitting, based on the fitting using the physical data, then you have to deal with what probability function. Then once you fit that, then you can determine then you can talk about the reliability of the system, the failure probability, so on. Okay. So that's the central limit theorem. This is one kind of the example, okay? And the sine wave with the Gaussian noise, sine wave with the Gaussian noise. So this is time t, and this is a x function, s function. Okay, it said st. It's a sine function. It could be going like that. Then life is harsh. What that means is even rotating machinery, it should have that should generate nice sine wave. But some let's say gear, if the gear tooth is wear out quite a bit, then there is a noise due to the wear, and some fretting occurs in there, which means impacting between the teeth. Then when you plot the rotating the wheels motion, it's not like a nice sine curve. Sometimes you have a lot of high frequency noise along here. High frequency noise is involved, which is really high, different frequency, much higher than the rotating frequency or gear mashing frequencies, vice versa. So over here it said, oh, this is, it should have way at the top x. So xt has is equal to noise plus rotating the sine wave harmonic functions. So one assumption, we know for the sine wave, we know the probability density function, we know it. Then the noise is usually Gaussian probability function usually fits well, because it doesn't have any particular kind of the trend for the noise. Noise is a noise. Usually mean is equal to 0. Sometimes mean may not be 0. It could generate a little bit slight positive or negative, the mean value in there. But compared to the sine wave, it's all about the zero mean for rotating machineries, things like that. Then I can say this is a normal distribution function or Gaussian probability distribution or density function. You can say that. For the sine wave, you know fairly well. You know this fairly well. So this is exactly that situation, and so he said n is Gaussian random noise, s is simply sinusoidal function with the phase shift. With the phase shift, depend on the situation, you can deal with the theta as a random variable. Even f can be a random variable. When you're dealing with a structural dynamics problem, then you're talking about the material property. Material property itself could be a random variable. What does it mean, random variable? Young's modulus is a random variable. From one batch to another, the variation of Young's modulus is pretty heavy, maybe by 2 standard deviation. That's bad. So then you can treat that as a random variable. Then you can compute what's the resultant effect because of that heavy variation of the material strengths. How to incorporate that in the finite element approach? How are you going to handle the variation of Young's modulus in solving problem using finite element? Not only nonlinear is important, variation of not only loading, variation of material property is a big problem. So think about it, what to do. There is no direct solution, but you have to think. And those, your thesis work should provide the answer, for example, for those situations. Here, in our department, as I mentioned, Professor Chang and I, we deal with probabilistic problems. I don't see anybody else, but we remember we are living in the physical world with a random, fully randomness in there. Everything is random. Your emotion is so random. Some evenings so happy, some evenings you are not happy. Variations. Yeah. So without proving, okay, I'm just going to give you, with this condition, I'm going to give you the probability density expression for the probability density function. If you look at the random data book, I have it up there. You're always welcome to come to my office and check out the book, you know, half a day or a day, okay? And random data, written by Julius Bandet. As I mentioned, he might be still living, but I don't think he is no longer working. I think he's over 90. But beautiful book. So the book, which is a thicker book, the book, application of correlations, functions, and all that, that's a thinner book. So this is good for reference book. The other book is good for a textbook about 2 semester worth textbook. And you can take a look. And here, this is there is an error here before. If you look at some addition, this was a 4. I think your note should be correct. Square root of 2 is correct, right? Not 4. And this is, as you look at it, what this distribution look like. As you see it, distribution is close to what? Normal distribution, isn't it? You see square root of 2, and you see the sigma here, summation, that exponential function you hear, and even minus sign there. And this is slightly different. But if you take a square of the square root of 2, then that's a 2. So it's really kind of a modified normal distribution function, because this is combination with a normal distribution with the sine harmonic kind of the distribution function. And sigma s, this is a standard deviation of s. This is sine wave, is equal to, s is a peak. S is a peak value, right? Capital S. Peak value divided by square root of 2. You should derive it. This is, you can derive it, pretty well known. So it has a direct one-to-one relations, and this is R ratio is given. This is ratio of the sigma s square, which is variance of standard deviation square, and this is same thing, but this is for noise, this is for real signal. And this ratio is telling you how much noise contamination in the system. If this is 0, what does it mean? If R is equal to 0, Sungwon out there? Sungwon, are you there? Do you hear me? Okay, you see me? Okay, all right. Well, what happened to Yongwon? Okay, all right, okay. Pay attention. And if R is equal to 0, what does it mean? There is nothing but noise, right? Sigma s is 0. Its real signal is not there. It's all noise. It's just full of noise. And if R is infinite, what happened? What does it mean? This is infinite. Infinite. No noise, because the denominator is very, very small, which means it's a brand new gear. It's mashing together, doesn't have a noise, it's very good. For the gear in the car, is no grinding noise. It's a very new car. So infinite means no noise. So it just goes between 0 to infinity. Probabilistic model, that's what you usually develop. Without the probability model, how are you going to handle that? So using, I don't want you to spend hours and hours to plot the case. Using this the equation form for probability density function, you can plot this. You don't have to plot every case, just to get your own satisfaction. No homework, nothing to worry about homework, but plot it, okay? And you see, what's this function look like? Huh? This is what function? Normal distribution function. That's the what case? For the noise in this problem. For the noise situations, what's the R ratio? R. For the noise situation, R is equal to 0, because this doesn't show well. This is a sigma s over sigma n squared. That's R value. That's equal to 0. Okay? Means signal. Sine signal is not there, but noise. But what about the probability model for the sine function? It's like this, right? So probability for the sine function this is minus x to plus x. It falls between, right? It's like this. This is the probability density function for the sine. So sine is there. For the sine, what does it mean? Sine, no noise, right? Only that one exists. So for the r value is concerned, is equal to infinity, right? Infinity means this, wait a minute. R is infinity is no noise. Right? No noise. When R is equal to 0, then sigma s, I'm confusing myself. So this is really for no noise case. It's only for, this is no noise. And this case is nothing but noise, right? And everything else is falls between here. And R is 1, R is 4, R is 9. R is 1, what does it mean here? Sigma n and sigma s is the same. So, you know, noise is pretty good. So this is dash dot dash. So dash dot dash, which is this is the one. Look like it. And R is 4, and R is 4 is right here. So if you try to plot R is 4, you should be close to that kind of the probability distribution, the density function. And R is 9. R is 9 means you have a strong toner signal. When I say toner, this is a strong, real signal is strong. So this is a dot. So it's like this. So when R is getting higher, it approaches to the toner signal, which is a sine. This model, people dealing the model. The goal is to develop the probability model. Without the probability model, you can predict. The reason you are using the probability function is to predict the engineering matters, predict the survivability of the system, predict the failure rate. You need a model. So one of the goals is to develop the model. To develop the model, you need a parameter to estimate the parameter. If it's a pretty symmetric, normal, then the business is simple. All you have to do is simply find the mean and standard deviation. If mean is equal to 0, all you have to do is get the RMS value or mean square value. That's about all. Okay, this is repeating almost 90% same. Change the infinite, the word infinite, to the finite. That's what I do here. N goes infinity. Mathematically, this is perfect. But in real life, we can deal only with a large. Then this is approximation. That's what I'm telling again. Then you need the statistics a little bit. So as you look at this representation, is good for, it said T1, good for what process? For stochastic process, it's a stationary process. For this case, algebraic process, right? One sample function represent the ensemble. So that's what you need here. Infinite number and finite number. But we are dealing with a finite number all the time. Again, random and bias error. So I'm going to stop right here for that definition stuff is concerned. And now some application of some sample problem to understand the random error and the bias error stuff. Just to feel a little bit. To deal with engineering matter. That's what I want to do. So phi or phi is experimental quantity. You designate the quantity. For example, why don't you name it? Experimental quantity. When you do the experiment, you designate, okay, I'm going to measure the pressure. And then pressure is experimental quantity. Okay? Lots of times, of course, you can deal with the pressure as a random variable. Random variable. But careful. Sometimes it's confusing, but nothing really to confuse. Why nothing to confuse? Process is, in engineering sense, process, random process, stochastic process. In engineering application, you are dealing with a time history. You are dealing with 0, t, acceleration, t, or pressure, time t. So you can dealing with, this is the first experiment, okay? You're dealing. Then that's a really process. You can deal with a sample record. It's a collection of many points, right? Many points. Then you can dealing with the ensemble. So you can dealing with a generally, okay, I want to just generally say this is x, but 1, whatever x is, 2, all the way. Then the whole thing is ensemble. Not the random variable. Random variable is when you're dealing the same the process here, dealing with at time t1. Time t1. I'm dealing with a time that point. I'm dealing with that particular point. That particular point. And that's a random variable. So dealing with the pressure or acceleration or velocity or strain at time t1, okay? Then a discrete point, you have to talk about it. Not the process. Process or sample record is whole history you're talking about. When you say random variable, you're dealing with a number, value. So here, the experimental quantity, let's say the x value at time t1. Here. So in this case, how many experiments? From 1 to all the way to, let's say, 10 here. He took a measurement at 10 a.m. every morning. Okay? The wingtip pressure. He just flew out there, and at 10 o'clock, at certain altitude, you measure the pressure, then plot it every day. 10 o'clock, same time, at time t1. Then every day, you're going to measure it. First day, second day, it changes. It's not the same because it varies. Wingtip pressure, of course, varies. Even temperature varies. Yesterday, 12 noon, the temperature is quite different from today's temperature at 12 noon. Everything is a fluctuation because of randomness. So I'm going to say phi or phi is just the experimental quantity, or just used here as a true value, whatever that value is. Phi, I use sometimes a phi or phi is also. It's a phi value is a true value. Sometimes you don't know. I don't know the true value, or may not exist, maybe not meaningful. If this is a temperature at 12 noon, it always varies. There is no such a thing. What's a true value for temperature at 12 noon? There's no such a thing. But mean value then has a meaning in there. Oh, mean value. Oh, mean value. I have a finite number of experiments. Then I just took a mean. So this is expected value of phi hat. Phi hat is estimate. Using the hat here is estimate. Phi hat I. First experiment, second measurement, third measurement, vice versa. Estimate, or actually the measure. So expected value or mean value, this is the mean of the estimate. This is available, or you can do it, right? Is 1 over n. This is equivalent to the probability density function. Summation I, and that's what that is. Then draw this, saying that's a mean value. If this is available, then you can say, there is a bias zero. Bias zero is expected mean value minus the true value is biased. Just notation used is B subscript phi hat is a bias error. Bias means systematic error. It's not the random, systematic. Okay. E minus 3. Bias error. And then you can define the random error. Random error is sigma. Think about standard deviation of estimate. Same thing, similar, limit 1 over n, summation, you wish, I wish n goes to infinity, but will never go infinity, then you have to live with error. Then estimate, ith estimate minus mean, constant. then square it. What do you call this inside here? What do you call this? If you name it. The variance of error, isn't it? Right? That's the variance of error. And when you take a square root, then standard deviation error of estimate. Standard deviation, strictly speaking, this is not true. The standard deviation of the random error of phi estimate, phi hat. You know what I mean anyway. So this is take away this guy. So that's why I put just to simply say random error of estimate. That's most proper name. Then this is random error. The other one is a bias error. Then now normalize it by the true phi. In your problem set, homework 1, from problem 6 to problem 10, I forgot to bring down the homework number 1 from 1 to 5 to return. Everybody did well except one, but I want you to look back. I can give it back Monday, it's not. Or stop by to my office, but you know, it's not critical anything. If it's a midterm exam, I have to say, okay, you come pick it up. Homework, I'll return Monday, okay? And this is the normalized, this is for the bias error, normalized by phi. This is a normalized random error. So using this error concept, I'll give you some problems. I gave some problem, then you should be able to do now. Okay, this is a probability still density function of a sample estimate, and this is what people uses based on the experiment. That's what their recommendations is, saying that if random error is less than 20%, this is a normalized random error. Assume the phi hat follows the normal distribution, but if this is the situation, phi hat usually follow normal distribution, except very different, except you are dealing very different physical phenomena, normal distribution follows well. However, for this situation, if the random error is less than 20%, then use a normal distribution. If it's higher, if this is higher than 20%, you have to be careful, because a model, probability model, affect the result. When you conduct the risk analysis, don't put everything in the normal distribution. You end up having wrong answer. Risk assessment, same thing. To generate the safety factor. Safety factor for nuclear reactor. I work at Argonne National Lab in Chicago area for 7 years before. And we don't know a lot of different things. What's happening, what's going to happen in nuclear reactor. Then safety factor, we boost it up. Can be 1.5. But safety factor, I remember, is about 3 or 3.5. where the safety factor concept coming in? Reliability analysis. So statistical analysis. That's the basis. So here, as we are dealing with Yun-Seok is dealing with plant survivability. If you push the wrong button from 1 to 3, it could be a super conservative. Instead, if you punch the 0.1, then very risky. It's all coming from statistics, remember. Safety factor, people using all the time for design. So sometimes very, very risky. So mu, this is mean of the error, mean error, okay? It's in previous page, phi plus b, phi hat, using that normalized the equation set. You can have this, replace this guy to that, then the standard deviation of the estimate is ER. This is the last line of previous page. You can have that. And the probability model for normal distribution is, this is exactly the form for normal distribution. Standard deviation, mean. This is the value, random variable, which happen to be the estimate. So put back this expression back into that final form. This is useful. So this error estimate, you will have a fun this weekend to solve all the problem. For first homework problem, all the 10 problem you could complete. Okay, I'll stop here. Then I'll see you, of course, Monday at 1 o'clock. Okay, so have a nice weekend and see you on Monday. Okay?